Good morning, good evening, good afternoon, wherever you are. My name is Sami Milki. I'm an otolaryngologist, aka ENT or ear, nose, and throat doctor. I recently bought a 3D printer, and I can assure you it's a lot of fun and a great way to waste money and time, especially. My kids love it because I can print them stuff. Now, for example, this Mandalorian helmet, all 3D printed. My kids love it. My eldest son is a fanatic of Star Wars, and it's great. However, I have to justify this great investment to my wife, and so now I'm claiming that I'm using it for medical education and for work. Indeed, I am the program director of the residency program at my hospital for otolaryngology head and neck surgery. And I keep looking for ways to improve education and training for my residents. One of the best known simulation we already do is cadaver temporal bone drilling to prepare and practice before temporal bone surgery such as mastoidectomy, cochlear implants, translabyrinthine approach for acoustic neuromas, etc. And I personally have spent countless hours drilling in the temporal bone lab. And it is essential before any resident touches any live patient for any live surgery. I remember less fondly the temporal bone harvest. We would all head out, residents, to the anatomy lab after the medical students were done with their dissections, and we would saw skulls to extract their temporal bones for many hours. And the smell of formaldehyde is not something I remember fondly at all. It's gruesome and it's not that much fun. But it was necessary if we wanted training material. So we would harvest about 80 temporal bone every year. So I'm proud to say that I'm the 3,000th person to brilliantly think about printing temporal bones. And so my next stop was Dr. Google, who informed me I'm the 3 millionth person to think about that. Nevertheless, I combed through countless publications on the subject, and I found a lot of material to guide me initially. Interestingly, a lot of the publications were done a few years ago, and at that time, the cost of these printers was still pretty high, and so it was cited in multiple publications that the cost was an issue. Recently, these prices have come down significantly, and the reliability and the speed of these printers have improved dramatically. The other issue is that every group of researchers would reach a different conclusion in terms of what is the best material to use to print these temporal bones, so that they would reproduce the correct haptic feedback when you're drilling them. So some would say polycarbonate, another group would say a special form of PLA, and some other group would swear by resin printing. There's even a consensus paper of sorts from the American Academy of Otolaryngology that is quite helpful, and I'll link it in the description. It's mostly written so that we do not reinvent the wheel, although that's what we're going to do. Either way, what doesn't exist is a YouTube video outlining the process from A to Z, so I'll try and do just that. There are a few things that are pretty cool about 3D printing temporal bone. Number one is that you can create a model that is accurate of a particular pathology of one of your own patients. You can print many of them so you can practice as much as you want on a specific pathology. Number 3, they don't smell like formalin. And number 4, with the proper setup, you can drill them at home. Number 5, it's fun. And number 6, it's only the beginning. You can 3D print whole heads with their sinuses and their larynges, and the sky's the limit with your imagination of what you can do for simulation. Now, in the spirit of full disclosure, I am not an otologist, I'm a head and neck surgeon, so apologies if I fumble some of the temporal bones anatomy. It's been a while since I've drilled any. And in this video, I'll try to go through the whole process of using your patient CT scan, segment it, extract the temporal bone information, make it into a file that you can 3D print, and then what are the settings that you should use to 3D print your temporal bone. And next, I'll show you some examples of temporal bones that I've printed, and one specifically that I have drilled. It's made of PLA. I've tried some other materials for printing, but I have not drilled them yet. And the plan is to get some of my friends who are otologists to try them out and give me some feedback to see which one is the best material, and so we can build on that. However, no matter what material you use, the process remains essentially the same. So let's dive in, and I hope you enjoy it. If you have any questions, you can put them in the comment. I'll try my best to answer them. Okay, so in this section, we will discuss how to use a CT scan to extract a 3D model to send for 3D printing. I'll be using a program called ITK Snap. There are multiple tutorials online by the people who create the program, and I'll link some videos in the description. But I'll show you here how it's done quickly. So first, you import your DICOM images from your CT scan. Next, you're going to use the automatic segmentation tool that is here. It's called Active Contour, aka Snake. So first you select the bounding box in all 3 dimensions. All right. I make sure that I captured all of the left temporal bone, sagittal view, done, and then coronal views, making sure I capture the whole length of it. Okay, perfect. Segment 3D. Now I'm going to use the method of threshold or thresholding. There are other methods, but for now we're going to use this one. We're going to switch to this view, and I'm going to pick the upper and lower thresholds. So since we're looking at bone, really, we're going to use the higher thresholds. These thresholds are essentially the Hounsfield units or the radio opacity of the tissues. So you really want to capture as much of the bone as you can, including the fine trabeculae inside the mastoid, while excluding the soft tissues. So if you lower the threshold, then you're going to capture more of the soft tissue. If you go up, you will capture more of the bone. However, you will lose the trabeculae. So you can do what works best for you and for the tissues you're trying to segment. So you have to play a bit with it. Play with the setting a little bit. I think this is okay for now. And next. Then you're going to put your cursor and then add something called a bubble. Just make it small so it's just in the area of interest. I'll put a few ones in multiple areas in the sagittal and the coronal views. So let's see here as well. Add bubble. Add another one here. Go into sagittal, see where else I want to add one. Here and here. And then we're going to go to next. So there are some parameters that you can play with, and you should just try different things. Not sure how it works best, but let's see. I think I don't want it to capture too much of the blue tissue, which is the soft tissue. All right. And then we start the algorithm. So it will iterate and it will grow the area in red. And it will essentially create this mesh that we need for our 3D model. So it captures the white, excludes the blue. Depending on your computer specifications, this process might be slow, might be faster. Will take a little bit of time. And once you're satisfied that it has captured most of the bone, then you can stop it. So you can watch it here in real time, how it's growing. See how in this area it hasn't really reached yet. I probably should have added a bubble. So what I can do is I can say, okay, finish. Let's see what it did. We had update here. And that's what we have so far. Not perfect, but that's the rough contours. And then you do it again. So again, same thing, same bounding box, segment 3D. Pick this, and then let's use the same settings. Small bubble, put it in the places where we still need it. Here, for example. Maybe put a smaller one here. And then next, keep the same settings and go. So see how the fine trabeculae here are not really being captured. I'm going to pause it. I might change a bit the parameter, maybe change the setting as well, smoothing and stuff. Do it again, because this will affect how it works. You can see there are some areas that are not being colored. All right, so let's finish here. Let's update. So this is where the tedious part can start, and it depends really on your use case. Are you using this model for just the outside surface, or are you using it to teach drilling to residents or to drill to yourself as residents or as attendings? The next step now is to really fix it manually. So zoom in. Let's see, for example, I'll give you an example. We want to get the ossicles that are here. So I'll zoom even further. Here we go. And then use the brush to manually. I like a round brush, small. Let's start where the ossicles start at the top. So here, you can do it manually, slide by slide, and that can be very tedious. And essentially, you can do the same for all the trabeculae in the mastoid. You could try and do it automatically by putting a bubble into the ossicles. Now the ossicles are small and they're only on a few slides, and so it can be done manually. It's not that tedious, but the trabeculae or the mastoid are pretty tedious. So if you're doing it for a 3D model to be drilled, you're going to spend a significant amount of time. So here is the vestibule, and this is probably the stapes foot plate. Keep following these bones. Now, probably the capitulum. There's something here. So malleus incus, that's probably should continue like that and like that. and then update. Now you might think, okay, how am I going to see it? Well, let's move around and go in. You can now see that we actually have the malleus, incus, and then the stapes. Over here. All right, so you do that slide by slide to really do all of the mastoid if you want, and you do it with as much detail as you want. You can use the automatic segmentation multiple times and it will help, but for the fine details, there's no way you can do it without having to do some manual work, and obviously it will lead to a more accurate model. Now that you're done, you're going to go to segmentation and then export it, and you export next as a STL mesh file. You name it whatever you want, mastoid probably, left, and you finish. And then I'll show you how it is in a 3D printing slicer. All right. So in this section, I'm going to use the 3D printer program that comes with it. For me, it's the Anchor Make Studio, which is based off Prusa Slicer. Now, whatever printer you have, you should probably use the same slicer that came with it, and probably have very similar settings. I've used a bunch of different slicers, and the functions might be named differently, but they do the same thing essentially. So we'll go. I've imported the model that we've designed. Now, in the other video, I actually was segmenting the left-sided mastoid, but in this case, I'm going to use a right-side mastoid just because there's an interesting quirk of that CT scan where the patient did have an osteoma. And so I spent more time finessing that model in the external auditory canal. So anyway, this model, I included, obviously, the mastoid, ear canal, styloid process, foramen lacerum with the whole path of the carotid artery. It goes up, horizontal segment, then comes out here. Sigmoid sinus, as you can see, comes down and then goes back up here before going to the jugular bulb. Internal auditory canal here. And that's our temporal bone. So now you want to be looking at the settings. So I use a 0.6 millimeter nozzle, makes printing faster. I also 0.2 layer height is reasonable. You can use 0.15 also, is also okay. It just will take a little bit longer to print. 2 perimeters means that your wall thickness is going to be 1.2 millimeter. And that's about it for here. For the infill, you should do 100%. There's a publication where they've looked at the best infill and they said 98%. So I'm not sure how they reached that number, but and I've tried 99 and 98 and 100%. They're pretty similar. I would say that when I've used 99, actually I've used 98 and I've used a cubic, I'll slice it for you and you'll see what I mean. The infill of the solid bone will have a different texture, have the texture, a cubic texture. I'm going to show it to you here. So basically, you're going to have that texture. Now, it is helpful to some extent when you're drilling that bone because then you know you're in infill, you're in solid bone. And then the texture will change once you get to a wall, like the wall of a cell, for example, because the wall of a cell, as you can see, there are 2 walls. So there's an inner wall, outer wall, and the texture changed. So it's kind of like in real life when you're drilling a temporal bone where the temporal bone has different texture. The bone has different texture. When you get close to the sigmoid sinus, the color changes. When you get to a cell, the color changes. When you get to the tegmen, the color changes, the pitch changes. So it's not a bad idea to have it like that. and I've drilled some bones that were like that, and that's not a bad idea. But I also think that it's not a bad idea to try with a rectilinear pattern for the infill, make it 100%, because technically the bone is 100% filled with bone. The other thing is that the skirt and brim, so what's skirt and brim is just, it helps with the adhesion, especially the first layer, for the first layer, not especially. And I'll show it to you in a minute. And then support. So ideally you want to get a model that doesn't need support, and there's a few specimens of temporal bone that don't need support. But then you have, for example, truncated styloid process in a way that it would print a bit differently and not need much support. But in this case, where I included all these overhangs, like these horizontal portions, just to follow the carotid artery, you're going to need support. Now, when you do support, I suggest you paint the support, because if you do just automatic support, it's going to do supports everywhere all the way up to here, and you don't really need that. It's not necessary. The other thing you have to make sure that you have checked is support on build plate only, because you don't want support on your model. First of all, it's going to degrade the quality, but the second thing is that it's going to create support for the inside. For example, in the middle ear or the ear canal, is going to make supports inside. You won't be able to remove them in post-processing. So just outside support. Organic, and I usually like to paint the support. So you use paint on support. I will look here, and I will just paint these areas that I know are highlighted. The other thing is, just want to make sure I don't get anything inside. So here, there's inside. So I'll just remove it. Let's remove all of this. And then paint just the outside. All right. And I'll show you what I mean. Highlight overhang. I don't know why I didn't highlight it. So I want to everything above 65 degrees of overhang being highlighted. So, all right. I probably need to add some support here. Here we go. So I'll go back. The rest of the settings, the speed depends really on the material you're printing. Just follow the instruction on the specific filament that you're using. PLA on these printers can print pretty fast. The faster you print, the lower the quality is going to be. And I think middle of the road. So this printer is capable of 500 millimeter per second. So I use less so I can get a better looking model. But you should play, you know your printer, you should play with the settings on your printer and see what works best for you. So I will now slice it. All right. So we can look at the slicing, and you can see it's like a CT scan essentially. You can see the air cells. The red is infill, solid bone. And I think I still managed to get these supports here going into the model. This I probably can remove, but could be difficult to remove. All right. So that's why it's critical you get your supports properly done, and then you send for printing. Now I'll show you how it looks like because I printed it. I'm holding the styloid process. That's it. 3D printed temporal bone. You can see the internal auditory canal here, the sigmoid sinus, mastoid, external auditory canal. It looks pretty good. And I'll show you now when I've drilled something similar, how it looks like. That's all for now. So that's the mastoid. You'll probably set it up To start, over here at the spine of Henle, down there is the silent process. Now that's another one we'll continue showing you here. Sigmoid sinus in here. Internal auditory canal in here. That is the stylomastoid foramen right here, where the facial nerve would be coming out. Jugular bulb and jugular foramen here. So after you've secured this into your holder, you can start drilling. And I will show you on a different model that is actually colored in gray. So again, that's the temporal bone and its holder. The holder is 3D printed, made of 2 parts with these clamps. And the tip of this is made from TPU, which is flexible and helps compress the material and hold it into place with better friction. All right. On my first attempt to drill that temporal bone, I used a 3mm cutting burr, and I started drilling, as I said, the spine of Henle. I was worried that the heat generated by the drill will cause the plastic to melt, and indeed, if you linger too long in the same place, that heat will soften the plastic and it will not feel natural. However, if you move further away for just a few seconds and then come back, the plastic will be solid all the time and it will actually feel like drilling into bone. So you can see in some places where the plastic seems soft, and that's me learning how to do it properly. The next day I used a 6mm cutting burr to speed up the process. If you remember from earlier, I was saying that the pattern of the infill matters, and these small white squares you see at about 5 o'clock in the image is the infill pattern, and that's 98%. So it is useful in a way that I know drilling into this pattern that I'm still in solid bone, and I can go further in and remove more material. Now with the 6mm, it's obviously much faster, and that's how you would usually start a mastoidectomy, a cortical mastoidectomy. The other thing you can see here is that I'm fumbling with the model with my hand, and that's because after a couple of hours of playing with it, I got pretty comfortable holding it in my hand instead of with the primitive clamp that I had initially, which was not the temporal bone holder that I showed earlier. And so you live and learn. So here I've already done a lot of the cortical mastoidectomy. You can see some of the air cells in the mastoid. That black spot that was there earlier, and that is where the external auditory canal is. Now obviously this is not ideal the way I'm doing it, and I'm doing it using a piece of plexiglass between me and the drill, so that way I will not be splashed with pieces of plastic. Although, as you can see, it doesn't really eject a lot of pieces. It creates that film, and for now it looks okay and I can still work. Now at this point I have advanced even further. I've opened the facial recess and I'm still working with the model in my hand. In this area, the plastic starts to get a little bit more annoying because it accumulates in these small recesses, and every now and then I had to pick them up with a small pickup. Now you can look at the model. I've opened the facial recess. You can see at 6 o'clock the sigmoid sinus had been skeletonized, and that metal pin is actually going into the stylomastoid foramen. Also on this view you can see down there where the incus would be, and putting this pin I would know whenever I got to the fallopian canal. And you will see how I'm able to actually recognize it even without going into it and seeing the metal. Because obviously, as I said, the texture of the bone changes, and I'll be able to really skeletonize the facial nerve canal, as you can see in here. So at no point is it breached, and I can see by transparency the metal into the canal. So now the mastoidectomy is complete, all the way down to the tip of the mastoid. The facial nerve has been identified. Facial recess is opened, and once I clean up nicely all these debris, the cochlea and the round window niche is also actually visible. You can also appreciate how thin is the posterior external auditory canal. So this is the final result. As you can see, we have the sigmoid sinus skeletonized. The incus and the antrum are easily seen. The facial nerve as labeled. The round window niche as well. And so that's the final result. So finally, to recap, this is another example of how it will look like into the holder, and the holder inside the box that you can use. Once you close it off, here I did with paper, but you can use tissue, you can see how it would look like, and the standard iPhone actually can zoom in significantly for you to be able to work off of the screen. That's the drill with the flexible shaft that you can use, and you can have it off the shelf. I use this setup with the plexiglass and with these 4.5 magnification glasses. All right, so in conclusion, I hope that you liked what you saw. I hope it was educational and you'll be able to replicate some of what you've learned today to be able to print your own temporal bone or any other bone or any other organ where it would be useful. This is obviously not something exclusive to ENT. I can already see how the maxillofacial surgeon could use it for orthodontic surgery, and I'm pretty sure they're already doing it. It's just not my specialty, so I didn't look it up. But in many other specialty, I think now with the prices going down, with the reliability, the quality, and the ease of use of 3D printers, there's more opportunity to use them for fun and for practice to improve our own skills as well as the skills of our trainees. I think it provides a cheap way to obtain training material and have them do whatever with it. They can break them, they can drill them, go through the facial nerve, go through sigmoid sinus. There's zero consequence. It's less expensive than cadavers. It's more readily available, and it's plastic, so it can be recycled. And speaking of the cost, these temporal bones weigh about 60 grams of plastic to print. And considering a spool of plastic is $20 for 1 kilogram, it costs about $1 to $1.2 to print. So it's pretty cheap, relatively. Now you do have to factor in the price of the printer, but a printer like mine, which is an Anchor, may cost between $600 to $800, depending on if you get it on sale or not. And there are much cheaper printers and much more expensive printers. Finally, as you saw also, there are different ways to drill them. Typically we use a microscope, but if you have 4.5 or even 3.5 magnification loops, that's more than enough to be able to drill a temporal bone. If you have a microscope at home, I don't know who has a microscope at home, but you can use that. An iPhone works well. You only need a 2 times magnification, and you can just drill off of the screen. What I'll say is that if you're using an iPhone, you really need very good lighting so that the camera will be clear and crisp. And you'll need good lighting either way, even if you're using loops. But that's something to consider. You can buy a strip of LED and put it in the box. The box can be 3D printed. The holder is 3D printed, and I can put the files into the description for download. So you could download everything, print everything. You'll need a drill. What I used is a Dremel drill, and it cost me about $100, $110 or $119, I can't remember. So it's not expensive, and you can use it and drill at home, have fun. It's very loud, so if you have a family or if you live with a roommate, it might not be ideal. So you need a soundproof room. More expenses. That's what I meant. 3D printing, lots of fun, lots of money wasted or invested. So I hope you enjoyed it, and tell me if you print anything and if it works for you.